Good afternoon, everyone. I hope everyone is enjoying re:Invent. Before we jump in, how many of you are familiar with our Inferentia product line? Great. And anyone catch Adam's keynote this morning? OK, good. A few of you. So there were a lot of exciting announcements, including the one I'm most excited about, Amazon EC2 Inf2 instances featuring our latest ML accelerator, Inferentia2. My name is Joe Sinertia. I'm a product manager on our Amazon EC2 team. Here with me today, I have two customers, Samir, a senior machine learning engineer from Qualtrics, and Srini, a senior software development manager from Amazon CodeWhisperer. They're both here to talk about their experiences with the Inferentia product line and how Inf1 and Inf2 is helping them improve performance and reduce the cost of their applications. Today, we'll take some time to talk a little bit about the AI and ML innovations that we see in industry and at AWS. Then we'll talk about how we're democratizing inference with AWS Inferentia, a goal of AWS as a whole to bring more machine learning to folks. And then we'll go into high-performance natural language processing inference with Qualtrics when Samir will come on stage. Then we'll jump back to talk more about Inf2 innovation in silicon and the distributed inference that Inf2 will support. And then we'll pass it off to Srini, who's working on some large language models that are dependent on this distributed inference. So let's go ahead and jump in. We've seen over a decade of innovation across artificial intelligence and deep learning on AWS. Using AWS services and infrastructure, customers brought their ideas to life. From Alexa's automatic speech recognition to Amazon's robotic automation to companies like Aurora developing their autonomous vehicle perception, and open source projects like Stable Diffusion, bringing image generation to many of our customers. There are hundreds of thousands of customers running ML on AWS, leveraging the scale and agility of the AWS cloud to reinvent their business with AI. And we see a flywheel effect that's starting to feed this period of rapid innovation in AI ML. Let's walk through the components that are propelling the AI flywheel. We'll start at innovation, as it's usually the spark that starts the cycle. AI, and more specifically, deep learning, has been around for decades, but started gaining popularity 10 years ago with the breakthrough that operationalized the algorithms to run more efficiently. By speeding up these dense mathematical calculations and increasing model accuracy, researchers opened new applications. And we saw customers start to find new ways to apply these innovations. Looking back at some of the earlier applications using convolutional neural networks to identify a cat in a video, or maybe a face in a picture. Then, as the variety of these use cases grows, so does the demand. And we see now more companies introducing AI services that delight their customers. With more demand comes more investment in new architectures, research, tooling, automation, and performance optimizations. And it creates a flywheel effect that self-propels AI growth. And let's review the latest trends that are propelling the flywheel forward. Customers are driving AI innovation at an accelerating pace to keep up with the applications, use cases, and demand. Possibly the hottest topic in deep learning is the explosive growth of large language models based on transformer architectures. In recent years, these models gained popularity due to their state-of-the-art accuracy and scaling properties, with some customers training trillion parameter language and computer vision models. Another critical enabler is the advent of self-supervised learning, which help data scientists tap into the vast wealth of unstructured and unlabeled knowledge available online, in turn helping to boost model accuracy and supporting training these large language models with billions or even trillions of parameters. The last element, but critical for innovation, is the state-of-the-art models such as Stable Diffusion, OPT, Bloom, or OpenFold becoming readily available via open source contributions. These open source contributions help increase adoption of new model architectures and often enable data scientists to improve model efficiency. And when we say AI models are getting bigger, we mean exponentially bigger. As shown here, the number of parameters in machine learning models has been growing at a staggering pace, roughly 10x per year, and even faster for some specific model types. And this curve is only getting steeper. These models are demonstrating new emergent capabilities that are unlocking even more applications. And here are just a few of them. Generative AI maybe the most popular category, with new models for image generation, such as one we just mentioned, Stable Diffusion. There's been breakthroughs in physical sciences, with models unlocking new mathematical solutions to problems that haven't been touched in over 50 years. There's also been exciting breakthroughs in healthcare and life sciences, with new open source models such as OpenFold or evolutionary scale modeling for protein structure prediction. It's an exciting time in the world of AI. But at AWS, we relentlessly pursue innovation on behalf of our customers. So we looked at this flywheel and thought hard about how AWS could create more value for customers and in turn add momentum to the flywheel. So we began making deep investments in every layer of infrastructure to support customers' AI workloads. By investing in infrastructure, we can provide hardware with more specialization, innovation, and security while decreasing the development timelines, which in turn means we can offer better price performance and new capabilities that unlock customer innovation. And so for AI workloads specifically, we made investments at the infrastructure level, but also at the silicon level, starting with Inferentia, then Trainium, and now Inferentia2. Inferentia and Trainium are purpose-built to accelerate machine learning at scale. Inferentia is a highly optimized accelerator for inference workloads, and Trainium is doing the same for training workloads. Both of these are designed from the ground up to deliver high performance and cost efficiency. Today, we will focus on the newest member of the family, Inf2. Inf2 instances feature the Inferentia2 chips that deliver more performance and take the title as the lowest cost deep learning inference in the cloud, and the first inference-optimized instance to enable cost-efficient inference for very large models. And to ensure that all of these new accelerators are easy to use, they are all supported by AWS Neuron, a software development kit which is seamlessly integrated into industry-standard machine learning frameworks. Neuron enables customers to quickly adopt our machine learning chips without changing the application or the underlying machine learning model. So let's take a walk through this journey. Inferentia was our first purpose-built ML chip that we launched in 2019. In terms of end-to-end performance, Inf1 delivers 25% higher throughput compared to G5, which is the latest inference-optimized GPU instance, and offers up to 70% lower cost per inference. This allows our customers to co-optimize for end-to-end performance and user experience, while at the same time dramatically reducing their operational costs. And we have thousands of customers to date that are leveraging the Inf1 instance, ranging from large customers like Snap and Airbnb to enterprise customers like NTT PC, Condé Nast, and also fast-moving startups. In addition, Inferentia runs most of the inference workloads for Amazon teams. These include teams like Alexa Search, the Alexa Voice Assistants, Recognition, TextTrack, and Prime Video. And we're excited about the cost savings and scale achieved on Inf1. Another recent announcement includes this ByteDance blog. They're a technology company operating a variety of content platforms, including TikTok and Douyin. They serve more than 2 billion monthly active users. They wrote a blog discussing their use of AWS Inferentia and how they achieved up to 60% cost savings and saw up to 25% better latency when migrating their models to Inferentia. And we also have a lot of internal teams enjoying the benefits of Inferentia. The Amazon Search product indexes billions of products, serves hundreds of millions of customers worldwide, and is one of the most heavily used services in the world. Since these searches happen in real time, they need the P99 latency to be under 10 milliseconds to ensure a delightful user experience. Using AWS Inferentia-based Amazon EC2 Inf1 instances for their transformer-based natural language processing models delivers latency under 3 milliseconds and saves 85% in infrastructure costs while maintaining strong throughput. It's rewarding to see customers get more performance at lower costs, and we're excited to build on this success with more AWS-designed ML silicon. Today, we're excited to announce the next generation Inferentia instances. The Inferentia2-powered Inf2 instance has 4 times the throughput and 10x lower latency compared to our Inf1 instances. Inf2 comes with 10 terabytes per second aggregated memory bandwidth across a total of 384 gigabytes of total accelerated memory. 10 terabytes per second. Think about it. That's 10 solid-state drives worth of data copied every second. That type of bandwidth really helps inference with models that are memory-bound. These instances offer support for dynamic input and control flow operators to help our customers optimize performance. Inf2 will come in 4 instance sizes. On the largest instance size, Inf2 48XL, you can deploy a 175 billion parameter model. Next, we'll take a look at how these specs come together to improve performance. So, 2 of the most important performance metrics we discussed for inference are latency and throughput. On the y-axis here, we plotted latency, and that's the time it takes the deep learning model to provide an output. And on the x-axis, we plotted throughput, and that's the number of inferences that are completed in a set period of time. Here, we plotted the top 3 inference benchmarks results for Inf2, the latest generation Inferentia instance announced today, and G5, a GPU-based instance optimized for inference. These benchmarks are for Roberta-based, a popular machine learning model used in natural language processing applications. As we see here, with G5, customers can choose to optimize for latency or throughput, but it's difficult to get high throughput and low latency. But with Inf2, customers can operate in this bottom right quadrant. That quadrant represents inferences that both provide high throughput and low latency. With Inf2, customers no longer need to make strict trade-offs on latency and throughput. With high throughput, you optimize the cost per inference, and with low latency, you get fast responses for better real-time functionality. And we see this performance across the majority of our popular transformer-based architectures, such as BERT or larger equivalents. Using Inf2 provides up to 2.6 higher throughput and up to 8.1 times lower latency versus G5, a price-performant inference-optimized GPU instance. The best part, all of these performance gains also come with energy efficiency. Since the underlying Inferentia2 accelerator is purpose-built, it is very efficient delivering high-performance throughput. Inf2 instances provide up to 50% better performance per watt as compared to G5 instances. A GPU instance optimized for inference. So what does 50% perf per watt look like in a real use case? Well, let's say we were building our own real-time document understanding application that needs to extract entities such as people or places, or I'll maybe do sentiment analysis as well, which is determining if the content is positive or negative in that document. And it does this for each document. So it's safe to assume that we might see somewhere around 1 million inferences per hour. And to perform these types of natural language processing tasks, we might use a transformer-based model, and these models contain dense mathematical calculations. So we likely use an accelerated instance such as G5 or Inf2 to get the best price performance. Well, let's say I was tracking energy usage to run these 1 million inferences. If I run on G5, I'm going to use 50% more power than I would on Inf2. By using less power to deliver the same results, Inf2 instances can help companies meet their sustainability goals. And now that we've heard a little bit about why we're excited for the Inferentia product line, we thought it would be best to hear directly from our customer using Inf1, Qualtrics. I'll now invite Samir, a senior machine learning engineer from Qualtrics, on stage to talk a little bit about their work on Inferentia.
Thanks, Jeff. Hey, everyone. My name is Samir, and as Joe mentioned, I'm a machine learning engineer at Qualtrics. Here at Qualtrics, we focus on experience management, building technology that helps close experience gaps for customers, employees, brands, and products. And we do this by leveraging machine learning in a wide array of domains, from classical machine learning with predictive modeling, forecasting, and anomaly detection, all the way through a suite of natural language processing and conversational analytics techniques. We really began this journey in 2019, when we had a fleet of small, simple models deployed on self-hosted CPU instances, which really limited our ability to deploy more complex models or to scale to the demand that we were seeing. From 2020 onwards, we began leveraging Amazon SageMaker and the GPU instances that they supported in order to scale out and deploy large language model-based NLP solutions. In 2021, we continued this journey, building out the Qualtrics machine learning platform with SageMaker as a key component, which drives end-to-end workflows for NLP, as well as end-to-end training and inference. In 2022, we've continued to scale both the types of inference and the complexity, as well as the number of customers that we are serving. And so we really began to look at optimizing cost and improving throughput in order to really scale. And we did this in two major aspects. First, model compression. We asked ourselves, how can we improve model efficiency while maintaining model quality? And second was Inferentia, in which we really asked, how can we leverage a wider variety or more specialized hardware in order to deliver higher price to performance for us and for our users? As a case study to show our results, we'll take a look at some of our NLP models, cross-lingual, multitask, and large language models that back a lot of the Qualtrics functionality, including Qualtrics Text IQ. These models are roughly a gigabyte in size and serve inference in more than 12 languages at the rate of hundreds of millions of predictions per day at low latency for the entire system. So first, we'll take a look at model compression. As Joe mentioned, the complexity and size of large language models has continued to increase over time. And with this increase in complexity comes an increase in computational complexity, higher latency, and lower throughput. So we took a different approach. We started to look at model compression in an attempt to reduce model size, reduce the computational complexity, and serve higher throughput on the same instances. Really, in the end, we achieved a more than 3x speedup with low degradation and a 15x speedup with less than 3% degradation in a paper that's forthcoming. But then let's take a look at Inferentia. Separately, we started looking at how can we take our large language models and deploy them on Inferentia and what benefits that they would have. We're pleased to say that on Inferentia, the relative throughput per dollar was more than 20% greater than on the G4s that we were previously deployed upon. And with this increase in throughput per dollar, as well as the ability to use a lower base capacity with cheaper, more affordable Inferentia instances, we have a projected cost reduction of 40% across these models. Additionally, this lower base cost has allowed us to deliver a wider array of ML functionality, some of which was previously unattainable or cost prohibitive on GPUs. In doing so, we've also built in resiliency to different instance types and flexibility to deploy on Inferentia, GPU, and CPU as well. But as we continue to use Inferentia more and more, we're also thrilled to see the reduced environmental impact, as Joe mentioned as well. Along the way, as is natural, we ran into some challenges specific to AWS Inferentia and Neuron. Specifically, runtime conversions and deployment optimizations around the multiple types of inference that are available. Parallel inference with model parallel, data parallel, and a variety of mappings to different neuron cores. And so we needed to benchmark and tune to really achieve the performance that we just stated. Additionally, a limitation in Inferentia 1 is dynamic sequence length, which required buckets and tuning to different bucket sizes to support a hybrid approach that allowed us to generate high performance on short text. What's next? We're continuing to roll out onto Inferentia, deploying our compressed models as well as a wide array of models onto Inferentia. But we're really, really excited about Inferentia 2. It's got the improved throughput and latency, as Joe mentioned, as well as increased memory. And two features that we've been really looking forward to are the quantization support with in-8 support, as well as dynamic input shape support, which will reduce our complexity to building and deploying models once they are trained. And with that, I'll turn it back over to Joe. Thank you.
Thank you, Samir. It's great to hear how customers are using and benefiting from the Inferentia product line. Now we'll transition to talk about the innovation underlying the Inf2 instances. So Amazon EC2 Inf2 instances feature 12 Inferentia 2 in a single server for a combined compute power of 2.3 petaflops at bfloat 16 or at float 16, and 4.6 petaops at int8. And these instances were purpose-built to deliver high performance, low latency for today's most demanding models, ranging from millions of parameters to billions of parameters. Let's take a look at some of the innovations that make this possible. So let's start with a quick overview of the Inferentia 2 silicon. Each Inferentia 2 device has 2 neuron cores, HBM2E memory stacks, and dedicated collective compute engines which allow us to overlap computation and communication when doing multi-accelerator inference. And each neuron core has a tensor engine, a scalar engine, and a vector engine. The tensor engine is optimized for doing matrix operations such as convolutions or matrix multiplications. The scalar engine is optimized for doing element-wise operations like ReLU or exponent. And the vector engine is optimized for non-element-wise vector operations, including batch normalization or pooling. We also have deeply embedded general-purpose digital signal processors inside the neuron cores. And they're tightly integrated with other engines. This enables dynamic execution, so control flow operators don't need to be unrolled or executed on the host. This design choice also allows customers to implement their custom operators in straight-line C++ and run them directly on the neuron core without the need to move data back and forth between the device and host. So let's dive a little bit deeper on dynamic execution. When we design hardware accelerators, we're focused on providing our customers the maximal achievable performance. But on the other hand, we don't want to compromise on flexibility, which ties into ease of use. Unfortunately, it is often the case that we need to make trade-offs on performance and flexibility. As an example, CPUs are programmable and highly flexible, but unfortunately, they're not designed specifically for workload like deep learning. Whereas hardware accelerators are extremely optimized for a given workload, but they're not as programmable. So to achieve the best of both worlds, we coupled a control CPU with a highly optimized purpose-built data path. The control CPU handles conditionals and loops, while the purpose-built data path does the number crunching at wire speed. This architecture allows the hardware to support dynamic execution, increasing flexibility without compromising on performance. And in order to improve flexibility further and further future-proof the design, we also deeply embedded vector processors inside the Inferentia2 neuron cores, compute units. When I say deeply embedded here, I mean that the processors have direct access to on-trip SRAM memories, which enables a blazing fast memory interface. To give you context here, most CPUs can access the memory through a bus of 256 or 512 bits per cycle. But these vector processors have an order of magnitude more memory bandwidth with 4,000 bits per cycle. This allows customers to execute custom operators directly on the neuron core compute units without needing to move data back and forth between a CPU and a coprocessor, and without even the need to move data between device to device memory, providing high flexibility at high performance. And one of the other major innovations on Inferentia2 is the data types. It will support 6 unique data types. Machine learning workloads require a massive amount of floating point calculations, and these calculations can be done at different levels of precision, ranging from floating point 2 through to the common 16-bit formats, float 16 or bfloat 16, and to the emerging float 8. Different networks require different data types to achieve their optimal accuracy. During early research and discovery phases, researchers typically prefer the ease of use of float 32. But then, as they ready a new ML model to run inference in production, they often optimize for price performance via more compact data types like bfloat 16 or even float 8, especially if it's a really large model that needs higher throughput or lower latency. By supporting 6 data types, we increase flexibility so customers can determine the performance and accuracy that meets their application needs. And so in terms of performance by data type, we've plotted here the theoretical values that Inf2 has versus our versus G5 GPU-based instance, and Inf2 has 110% more bfloat 16 compute performance compared to G5, and 4.3 times more tfloat, TensorFloat 32 compute performance. As you can see, selecting a higher precision data type, such as float 32, reduces the petaflops, but with 4 total bytes, it provides the highest accuracy. The key element here is that we're enabling our customers to pick the most optimal data type for their use case, where the trade-offs are throughput, latency, and accuracy. So we discussed innovation at the silicon level, but we're also defining new features at the server level. Inf2 instances are the first inference-optimized instance on Amazon EC2 to support distributed inference with direct, ultra-high-speed connectivity between accelerators, which also enables 10 terabytes per second accelerator memory bandwidth. So this high-speed inter-chip communication is critical for the collective comms required to support very large models using distributed inference. And so we talked about this slide a little bit before. Do you recall that growth in model size has been explosive over the last few years? Well, we built Trainium to offer the best scalability and performance for training these very large models. But let's talk about how Inf2 optimizes inference for such large models, especially when they simply will not fit into a single chip. So you may all be familiar with the distributed training techniques, as this become popular for billion or even trillion parameter models. But let's cover why these techniques are also important for inference. As you can see from the simple illustration, as model parameter size grows larger, in most cases, this means the model was designed with deeper, denser layers during training. The number of parameters is one of the most important factors driving the amount of memory needed to store the model. Now, there are other important factors, such as the data type, but for example, we'll hold all of those equivalent. Under these assumptions, there is a roughly 500x difference in memory required for these two models. And so let's take a look at how we deployed a 300 million parameter model. So there's several cloud-based hardware accelerators available that can fit a 300 million parameter model in a single worker. While these were considered large models 3 years ago, today we see them frequently in production. They run on existing hardware accelerated instances such as Inf1. But when we're looking at models with billions of parameters, they require even more workers. So the only option is to use a technique known as model parallelism, here more commonly or more specifically tensor parallelism, to split the model across several workers. To understand why this is possible, let's take a high-level look at the math for the neural networks. So we'll come back to our basic fully connected artificial neural network. While this is a nice graphical representation of a neural network, it doesn't help explain how to split layers across workers. Instead, we could think of the fully connected layers of a neural network as a set of dense matrix multiplication calculations, simplified here for explanation. And using this matrix format, we use the properties of matrix multiplication to split the computation even further. We can see that both of these are mathematically equivalent, but now different workers can complete different portions of the computation. However, when we divide these computations, we still need to sync the values across each of the workers. So you see the arrows here indicate computations that were completed by an independent worker. So they now must be summed across all of the accelerators to complete the inference request. So we designed a ring topology with direct, ultra-high-speed connectivity between accelerators. With this ring connectivity across an Inf2 instance, we're effectively built a 384 gigabyte accelerate memory pool with 10 terabytes per second bandwidth. So Inf2 provides high-performance, low-latency inference on today's most demanding 100 billion parameter models. And bringing all of these innovations together, we have the most price-performant inference-optimized platform available on AWS. Let's take a quick look of how Inf2 performance stacks up against G5. Again, a GPU optimized for inference, and readily available on AWS today. For OPT30B, that's a 30 billion parameter model, Inf2 delivers 573 tokens per second compared to 181 tokens per second on G5. That's over 3 times the throughput for this example of a large language model. Now, let's take a look at even larger models, such as OPT66B. As you guessed, that's a 66 billion parameter model. Inf2 delivers 248 tokens per second. But here, something else happens. G5 only has 192 gigabytes of total memory, as compared to the 384 gigabytes we see on Inf2. So we see G5 run into added memory issues as the models reach 66 billion parameters, whereas Inf2 is still delivering high performance. That's because Inf2 was purpose-built to serve these types of large language models, delivering high performance, low latency outputs at the lowest cost on Amazon EC2. And so we're really excited because our internal customers have already seen great performance results. For example, Amazon Search tested their billion parameter model and is seeing 2x the throughput compared to G5. According to Amazon Search, these larger pre-trained encoders have a higher capacity to encode the rich information in the data, leading to higher accuracy. However, serving larger models can be prohibitive in real-time production systems with strict latency requirements, such as search, ads, or recommenders. Reducing 1 billion parameter encoder inference latency to a single-digit latency opens up the possibilities for these and additional applications to leverage the benefits of large models for better customer engagement and reduced deployment costs. So how can customers take advantage of all the innovations in Inf2? Well, accessing all of this performance is easy with the AWS Neuron SDK, which is the software development kit, as we talked about before. And Neuron integrates Inferentia2 into popular machine learning frameworks like PyTorch and TensorFlow. This enables customers to bring their model as is and seamlessly compile them to Inferentia or Trainium with only a few lines of code. The Neuron SDK includes a compiler, runtime, and profiling tools. Our goal here is to provide our customers with good performance out of the box with no model changes or performance tuning on their part. And we constantly work to improve Neuron. Over the last year, we've added support for distributed training, eager debug mode, collective communication optimizations, and a few more. And by using Neuron, you will also keep getting new speed up over time. As we optimize the stack more, we often hear customers using Inf1 and TRN1 that after updating the latest Neuron drivers, they see a noticeable out-of-the-box performance improvement. So Neuron makes deploying a model on Inferentia as simple as possible, and we put a lot of effort into that. Here, for example, you can see that we download a Hugging Face vision transformer model with just a few extra lines of code, highlighted in the red boxes. We compile it to Inferentia and deploy it at a high performance. We don't require model tweaking or data type conversion. Just bring your model as is, and Neuron will run it. And we also know how important it is for monitoring and debugging tools when deploying models. Inferentia has an extensive tool set for monitoring and debugging. This includes Neuron LS for device discovery and topology information, as well as Neuron Top for real-time visualization of the neuron core and vCPU utilization, host and device memory usage, and breakdown of memory allocation. This information is also available in JSON format, which can be used with popular visualization and deployment monitoring tools like CloudWatch or Grafana. So now that you've seen the performance and how easy it is to just get started, I'm going to hand the mic over to Srini from Amazon Code Whisperer to talk about the innovative work they're doing with large language models and how Inf2 will help address their challenges.
Thanks, Joe. Quick show of hands. How many have used or heard of Code Whisperer? OK, by the time I'm done, I'm hoping that we'll all go give it a try, and then we'll be able to do this. When I started coding 20 years ago, there was like a few languages, few services, and few frameworks to work with. But nowadays, for developers, there is so many different programming languages. There's different services that you integrate with. And to do all of this, there is also the design patterns that each of these services and the languages follow. So for developers to switch from one to another and be able to do full-blown service integration is a Herculean task. This is where I think some of the AI and ML technologies will come in handy for making the developer productivity better. To add to it, there is a lot of boilerplate code that developers have to write to bootstrap the instances and bootstrap the code and services as well. So Code Whisperer is an ML-powered coding companion. What essentially it does, we've trained the Code Whisperer system on billions of lines of code. It easily integrates with all your IDEs. We have support for Visual Studio Code, JetBrains, a family of IDEs as well. Right now, we support C#, TypeScript, Python, Java, JavaScript. At least at reInvent, we announced C# and TypeScript support. So if you're one of these developers, then you use this on an IDE, and then it recommends code suggestions. Not only does it do single-line completions, it actually does full function block completions as well. This is a quick demo where you write a bunch of comments, and then Code Whisperer will start recommending code suggestions. It uses the context of your IDE or file based on your comments and the existing code, and then you're able to see the recommendations. We actually support up to 5 code recommendations because as you're working through code, you decide what sort of functionality you want and what parameters you want to be able to use. And whichever recommendation that you want, you're able to pick and choose that too. There is a feature called reference tracker, which is probably very, very important to pay attention to. Because this system is trained on open source data along with some internal Amazon data as well, there's a chance that we replicate code from one of these open source sources. So what we essentially do is we provide attribution if the code is unique enough, where you as a developer could choose to use the recommendation or not. We also show licensing information as well. Like, let's just say as an example, I do not want to use Apache license in my code, then I can reject the code recommendation as well. All of these settings are provided in the code recommendations as well. Within Amazon, there is a lot of developers already using Code Whisperer for developing. In fact, my own team, it's kind of cyclical effort. The developers building Code Whisperer are already using Code Whisperer to code. Now, like you can all assume, behind the heart of Code Whisperer is this large language models. In the last few years, like Joe has been talking about, these models have evolved quite a lot in terms of both the frameworks, in terms of the parameter sizes as well, how big they have gotten. We have, for Code Whisperer, also rely on some of these models. We are using decoder models, encoder decoder models as well for different use cases. There is the code generation, there is the code explainability as well, for which we have run a lot of experiments in terms of how we've tuned these models. Once the model is trained, the 175 billion model that people are talking about and the 100 billion models, now you get to the optimization of all of these models too, for you to be able to deploy these models. So for Code Whisperer, we have used quite a lot of techniques, all the way from model parallelism. In our case, we use tensor parallelism. We do distill the model into smaller sizes as well, and then we use different precisions. Like I think Joe was talking about, we started with a much larger precision, and then after the model is trained, then we get to smaller precisions to be able to use it. And then finally, there is compilation, which we're experimenting with as we move forward too. The primary challenge is, like for anybody who's tried deploying any of these models, we kind of categorize into 3 buckets. There is the cost optimization that is important. For us at Code Whisperer, I think the other use case is latency. As you're coding in your IDE, you want very snappy, very fast recommendation to show up, which means we're looking at millisecond latencies for the inference to be served from. And then finally, for the developers on my own team, they want the ease of deployment. Ideally, you want to be able to train the model, take it and host it, and then get the recommendations so that you can focus on doing other things as well. So we, for now, have been trying different techniques all the way from deep speed and how we implement some of these. Where Inferentia comes in handy, Inf2 specifically, given the models that we're doing for us, the neuron link that Joe talked about earlier, where there is the chip connectivity. Even after training these models and optimizing this model to be much smaller, we do expect this to span multiple chips, multiple GPUs of sorts. There is no way we'd be able to host it on a single GPU or a chip at this point of time. So for this, the Neuralink, the link ring connectivity that Inf2 has is going to be a huge benefit, because then the latency of us being able to host it on multiple chips will be much smaller than us having to do something else. That's one of the most important things that we pay attention to. And then the Neuron SDK, which kind of actually makes it very, very easy for us to go compile the model and then deploy and host and start serving the models as well. At least on the Code Whisperer side, we're looking forward to being able to migrate a lot of it for our hosting purposes into Inf2. What happens with the throughput being better on Inf2, the cost per inference and how we are going to provide recommendations to the developers is going to go drastically down, which is what, for us, will be useful as we scale this into a full-blown available service and start serving millions of customers.
Nice. Thanks, Srini. It's great to hear how large language models are actually coming out to play in new products at AWS. So just a quick wrap up here. Wanted to leave you with 4 key takeaways. So high performance at low cost, significant latency speedups, designed for distributed inference, and easy to use. So when we design Amazon EC2 Inf2 instances, we design them to deliver high performance at the lowest cost for deep learning inference on Amazon EC2. And part of this performance is significant speedups on latency, including 10 times lower latency for Inf1 and up to 8x lower latency versus G5. And we also have Inf2 purpose-built for distributed learning for these super large language models. And lastly, as we talked about with the Neuron SDK, it's easy to get started. So there's nothing stopping you other than downloading an open source model and deploying it right on to Inf2. And just to wrap up here, we have a lot of sessions around both AWS Inferentia, AWS Trainium. We invite you to scan one of these if you're interested to learning more. We have workshops to chalk talks to breakout sessions. Thank you very much.